Okay, so let's see when we go to another orbital what the effect of the orbital is on the wave function. All right, so if you recall, right, there are different changes in the wave function in the one-dimensional particle and box when we change the quantum number from n equals 1 to n equals 2, right? Specifically, we started to see features called nodes, right? And so we get a similar effect when we change the n, which in this case, the principal quantum number, right, from 1 to 2. So we're changing from a 1s orbital to a 2s orbital, okay? And by doing that, we are changing the principal quantum number from 1 to 2, all right? So in a similar fashion, we expect to start seeing appearances of nodes. And so here's the mathematical function for the R2, for the radial function of the 2s orbital, okay? And so again, we have an exponential term, and then we have a pre-exponential term here. This looks very familiar from the 1s orbital, but we see a new term that's right here. And what this means is that the value, because this term is here, what happens is you end up with a point at which R2s can be equal to 0. And so R2s, right, the radial function will be equal to 0 when 2 minus theta equals 0, all right? Because that will turn to 0 and that will multiply out and the whole term, the whole function will become 0. All right, so in other words, right, this occurs when theta equals, or theta equals 2, okay, equals z times r over a naught, okay? So that's dependent on, that's going to be dependent on, again, the nuclear charge, right? And so what we're looking at, so as an example, let's back up. As an example, right, if the nuclear charge is 1, such as for a hydrogen atom, then when the radius is twice that of the Bohr radius, then we expect to see a value for 0 for R2s. And so we could actually just put this here, where we have, or R over A naught equals 2 over z. So this point is 2 over z, comma 0, okay? In terms of this axis, okay? These axes, all right? So we expect, in other words, we expect a crossing point in our function here, all right? So again, we have an amplitude here, and what the function will look like, the wave function, the radial wave function will look like, is it'll go through this crossing point. We erase this for clarity. Find a global minimum, and then return and approach the axis, the x-axis, as it approaches infinity, all right? And so this is what we have the wave function look like. Again, we have this crossing point where we will not have any probability of electron density, and so that becomes a little bit easier to see when we actually look at, when we square this and we replot this, right, as R over A naught, and R squared, R squared, all right. And what we end up with, whoops, 4 pi. And what we end up with is oops, at this point in the wave function, what we end up with is a probability function that looks like this, okay, for the 2s orbital. And so we have a point at which electron density will never be found. So in addition to at the nucleus, we have another point, right, of radius r at which no electron density will ever be found. And so this is very similar to the one-dimensional particle in the box, and that is a node, okay? And what we see is we have two local maxima, where at this point, okay, above at a longer distance than where this node is, we have the highest probability of finding the electron. But we also have a local minimum closer to the nucleus down here, and that will become really important when we discuss the relative energies of these orbitals when we talk about the relative energies of these orbitals when we talk about Aufbau principle.